In particular, here notice that I have a M given A and I have a J given A and A given BE, then P of E and then P of B, and in this side basically these two will be multiplied, these two will be multiplied, added, these two will be multiplied, these two will be multiplied, added, those two will be added. Agreed? That's what you are actually doing in the background. Then I will point out that within this computational graph, you are doing redundant work. What is redundant work? You are multiplying the same numbers again and again. And there is no reason to multiply them second time. If you multiply them once, the answer will be the same the second time. Right? And so you remember. Okay? So in particular, you notice that PJA and PMA is being multiplied twice. So the first time I multiply it, I'll remember it as a factor in my memo table. And the second time I need to compute something, I check if it's already been computed. How many of times? You have done this many times in your programs. This is basically dynamic programming. This is basically memoizing. It's not even full-on dynamic programming, it's just memoizing. This is the idea called variable elimination. In particular, what happens essentially is you start remembering these intermediate factors. And once you compute the intermediate factor, the second time around you don't have to compute it, you just look it up. And you call them factors rather than probabilities because they're not probabilities. Remember we talked about this, you multiply some of the computational CPT tables. After everything is multiplied, you will get a probability distribution. The middle results are not necessarily probability distributions. Okay? The interesting final question with respect to variable elimination algorithms is how big can these stored factors be? In your memoizing, you get some amount of memory to memoizing. If you wind up memoizing by remembering the entire joint distribution, then you are wasting too much space. In particular, it turns out that the order in which you eliminate variables, the order in which you kind of marginalize over variables, variable elimination means marginalization over the variables, can lead to smaller versus larger intermediate factors. And the optimal order, if you do it in optimal order, you'll wind up computing the smallest intermediate factors, which means essentially A, you do less computation, and B, you have less storage to put that factor. Do you see what I'm saying? Okay? So it turns out that variable elimination algorithms try to optimize the order in which to eliminate, marginalize the variables. And the question would be, why not compute the optimal order of elimination of variables? The answer, whenever there is any such question, is, well, the only way to do it is check out all the orders. So optimal variable elimination order is NP hard. Computing the optimal elimination order is NP hard. But getting a reasonable one is not that bad, is not that hard. In general, if you actually happen to eliminate them in the more or less topological order, then you get a pretty good size on the factor. That's the background on the variable elimination. Okay, I don't expect you to have understood. I basically only want you to understand that variable elimination algorithm is essentially an improvement on this first order. This you should understand. You should be able to go home and you should be able to get this number out yourself. Okay, if you don't, then at least you don't even know any single idea. In fact, if you do this, you already know the zeroth idea, which is writing the entire joint distribution and looking up all the numbers. And then this is the second one, which is slightly better. And then the other one, of course, is essentially going to remember variable factors that I didn't go into the details. But that is actually more or less the state of the art exact inference algorithm. And that leaves the other half of the inference algorithms, which is essentially sampling the network. Okay? Which is essentially sampling the network. So let me give you an idea, and then I'll most likely give you the videos to watch for this idea. Okay? So the idea would basically be, imagine I'm trying to compute some particular joint distribution entry in this table. Okay? What I need to do is, suppose I just wanted to compute, some probability. To compute that some probability, I'll sample this network. Sampling this network, the first idea would be sample the entire joint entry. Okay? Suppose I want to sample the joint entry, I will start from cloudy. I will sample the value for cloudy. Now, the way to sample the value for cloudy is that the table is telling me that probability of cloudy is 0.5. That means I need to get myself a coin which comes heads 0.5, tails 0.5, toss it, and if it comes heads, I say cloudy. If it comes tails, say not cloudy. The tossing is very important. Then imagine that I got the cloudy, right? Then, suppose it turned out that it came heads, so I have cloudy. Now I need to sample sprinkler and rain. The idea is by the time I come to sprinkler, I already know cloudy's value. Okay? If the cloudy is true, which it is, the probability of sprinkler coming on is 0.1. So now I need another coin, which comes heads 0.1 probability, and tails 0.9 probability. This is basically coin tossing can be implemented as a random number generation. Like for example, if you generate a random number between 0 and 1, every computer will have a random number generation between 0 and 1. And that number will essentially tell you the probability. Okay? So for example, in this case I generate a random number. If it is more than 0.1, then I assume sprinkler is off. If it is less than 0.1, I'll assume sprinkler is on. That's computer tossing. And similarly, I come here, the rain I will try to do this with respect to the rain I will try to do this again with respect to cloudy. So I need 0.8 probability true. So I again call a random number between 0 and 1. If it is greater than 0.8, I'll assume rain is on, rain is off. If it is less than 0.8, I'll assume rain is on. Okay? I'm sampling every time. Notice the sampling is important. Okay? At that point, imagine that I had this, so that I wound up, when I actually sampled, remember 0.1 sprinkler will be on and 0.9 sprinkler will be off. That's why more or less with high probability sprinkler was off. So in my sample, the sprinkler was off. It doesn't mean that the sprinkler will always be off. I actually have to see by tossing the coin. Okay? And then this was on. And so at this point I come to wet grass. Its parents are known. You see what I'm saying? And so I actually know which coin to toss. This is generating a single sample from the network. This is a single joint distribution sample. Now, if I know how to do this, then if I just wanted to compute probability of, let's see if I can do this. This is basically joint distribution. If I wanted to compute, in this case, if I wanted to compute a conditional probability of something given some other variables having that value. Okay? Then what I would do essentially is do rejection sampling. That means I sample a whole bunch of these joint entries, see the number of entries where, if you are trying to compute A given B, let's say. So you take the number of entries where A and B are both true. Put that in the numerator. number of entries where B is true, put it in the denominator. That will be your estimate of the conditional probability. It's called rejection sampling because any entries that you generated where the evidence wound up being not holding, so you said probability B given E, and when you generate the joint entry, you may get not E. So that is thrown away because it doesn't help in the numerator nor the denominator. So it's wasted effort. This is called rejection sampling. The last great idea is likelihood weighting, which basically says do whatever you were doing before. Now, instead of saying a sample is a whole sample, you can start having fractional samples. Let me complete that idea and then we can go up. I'm sure it will take 2 more minutes. So the same thing, except imagine I'm trying to compute some probability given sprinkler is true and wet grass is true. So I want a conditional probability of, let's say, cloudy given sprinkler is true and wet grass is true. So any sample where wet grass and sprinkler are not true is a wasted sample. Do you understand what I'm saying? Suppose I'm trying to figure out what fraction of people who smoke get an A in this class. So all bozos who are not smoking, useless. You see what I'm saying? So I have to basically look for smokers and then see how many of them get A's. So the samples where evidence is not holding has to be rejected according to the previous one. What happens here is you will essentially compute a sample which has a fractional value. Cute idea. Okay, so here is the idea. So you start as usual before, cloudy, and you are now trying to generate a single sample. Okay, in this case cloudy is true. And then at this point, given that cloudy is true, I definitely need sprinkler still has to be true, because if sprinkler is not true, it won't be a useful entry. It won't be in the denominator or the numerator. If in your life you are not contributing to either numerator or denominator, you are useless. Contribute to something, right? So then what I'll do is I need to contribute to sprinkler being true. If I actually toss a coin, sprinkler might be false. So I do wishy-washy thing. I'll say, okay, sprinkler has to be true. Well, if I, clamp sprinkler to be true, I need to assume that that only happened with 0.1 probability. So I was trying to generate an entire one weight sample. Now I suddenly have reduced my hopes and say I'm generating a 0.1 weight sample. Okay, and then basically I come to rain. Rain is not clamped, so I can basically sample it the way normal way. And then it turns out that rain actually has been sampled to be true. At this point I need to sample wet grass, but I don't want to sample it. It has to be true. But I know that sprinkler has been made true by agreeing with a 0.1 probability. Rain is already true because of my luck. Okay? So if sprinkler is true and rain is true, wet grass can be made true with 0.99 probability. So my weight of my sample now is 0.1 times 0.99. That means 0.099. So I can use this sample because this is a sample where the evidence holds, so it can be adding to the denominator. Does it also add to the numerator? Well, if I'm looking for cloudy, yes, it adds to the numerator. If I'm looking for not cloudy, it doesn't. Do you guys see what I just did? This is one of the first great ideas of sampling-based inference, because you are not wasting any sample. You are considering fractional samples. Real world doesn't give you fractional samples. You could only do it because you have the CPTs. And this is what is called, these weights are called likelihood weights. And of course I told you how to do this sampling, proving that if you do this infinitely often, you get the actual probabilities. That is the theorem. The textbook actually proves that in fact that will converge to the actual probabilities. Okay? This likelihood weighting is a great idea. In fact, I'll go through it slowly in the videos I'll send you. Okay? And the last one I won't mention at all is this Markov chain Monte Carlo, which I kind of mentioned earlier, where you sort of sample a network given its Markov blanket. I mean, sample a variable given its Markov blanket and keep doing this. And what happens then essentially is this entire network is in different configurations, and those configurations sort of loop between each other, giving rise to a Markov chain. And if you compute the steady state distribution of Markov chain, from that you can compute probabilities very fast. Okay? I will stop here. I will certainly send you the videos that you can watch just for the sampling part. Okay? Let me stop because we're already way too late. Eat some more, and if you need to ask me questions, come on.